When a dynamic system takes a direct, high-velocity hit, the underlying mathematics of its survival are immediately exposed. Most patterns break under the strain. Without a structural anchor, trajectories deform into a chaotic tangle of unrecoverable noise. A robust system absorbs the shock and returns to its baseline path. It preserves its organized content even as the surrounding environment fluctuates. Unified harmonic systems defines a cycle as a strictly constrained reaction-transfer organization, distinct from simple spatial repetition. Durability is the only metric that matters. A loop earns the title of cycle by surviving bounded perturbation. The core analytical task is separation, distinguishing coincidental, transient looping from a genuine structural anchor. The framework employs 3 sequential mathematical admissibility gates to verify this persistence. A local loop becomes a foundational building block for the larger continuum only after clearing all 3 thresholds. The first gate establishes the baseline for recurrence, the empirical limit cycle attractor. Judging whether a cycle persists requires a continuous, hard diagnostic test rather than a subjective observation. Stability is tracked through the largest non-trivial Lyapunov exponent, denoted as lambda-1. This phase space visualization shows a limit cycle. To pass the first gate, equation 803 requires the exponent remains strictly less than 0. When negative, the orbit is phase-locked, forcing the system back to established timing and rendering it immune to drift. But environmental stress can push that parameter up. If the exponent crosses into positive territory, the limit cycle instantly unravels into chaotic slipping. At this exact moment, the local structure is permanently rejected. The negative Lyapunov constraint safeguards the system, preventing the construction of complex architectures on unstable foundations. Once a cycle proves its phase lock, it faces the second admissibility gate, balancing its internal damping against the external environment. Traditional models often frame dissipation as a destructive force, but unified harmonic systems treats it as a structural requirement. This diagram represents the energy balance integral, mapping the exact velocity of transfer bounded within an external reservoir. Here, dissipation acts as a shock absorber, compressing harmful overshoot excursions so the system can safely recur. The external reservoir facilitates this by keeping the cycle's inflow and outflow bounded. However, if the reservoir becomes overwhelmingly sink-dominant, equilibrium breaks. This extreme dominance weaponizes internal damping, stripping away structural support. As support drains, the cycle's amplitude decays until the loop flattens into a dead, non-cyclic transient line. Persistence depends on maintaining a bounded equilibrium between internal damping and external reservoir exchange. The third constraint scales the perspective upward, moving from isolated loops into hierarchical, nested architecture. Consider a high-frequency, localized cycle operating at the microscopic level, a tight energetic core driving the rotation of a massive, slow-moving outer ring. The inner loop dictates the gating conditions, controlling the distribution patterns and the timing of the slower global loop. The system's stability depends on a rigid phase link, a mathematical bridge binding the fast inner cycle to the slow outer cycle. The 2 scales can operate at different speeds if their relative phase remains aligned. But if stress forces this timing to slip, the geometric phase link shatters, the nested architecture fragments, and the outer ring collapses, even if the inner cycle continues spinning independently. The emergence of complex system architecture in UHS is bounded by the preservation of these cross-scale phase links. Once a nested cycle clears all 3 admissibility gates, we test the surviving structure against classical thermodynamic language. This chart maps the harmonic cycle against traditional thermodynamics, comparing entropy against structural loss and renewal. Within standard, slow-moving regimes, traditional definitions of sources and sinks map perfectly to the cycle's behavior, resulting in a stable delta S reading. If the cycle transitions into a highly driven, fast-switching boundary regime, the environment alternates too quickly for traditional measurement. This creates a thermodynamic mirage. The classical overlay flashes errors, failing to process the speed of the source-sink alternation. Despite these classical errors, the underlying harmonic cycle remains mathematically stable. This precise mismatch identifies classical thermodynamics as a constrained interpretive layer, a useful lens rather than the absolute identity of the system. With the cycle stability verified and its mapping constraints established, Chapter 8 prepares the system for its handoff to Module 9. The framework now enforces a strict filtering rule. All raw trajectory histories and fragmented local noise are explicitly discarded. We compress the data into a single output, retaining only the recurrence class, persistence margins, and failure boundaries. A cycle serves the broader continuum only once it is mathematically verified as a truly unyielding, persistent anchor.